In this video, we're going to be talking about Le Chatelier's principle. Now, Le Chatelier's principle simply states that when a stress is placed on an equilibrium system, so when a stress is placed on an equilibrium system, so this is going to just be an equilibrium reaction. So when you place a stress on an equilibrium system, the system will respond to minimize the stress and get back into an equilibrium. So the equilibrium reaction is going to respond to the stress, minimize it by getting back to equilibrium. In this class, we're going to talk about four stresses. And the first one we're going to talk about is concentration. Then we're going to talk about pressure, temperature, and finally, the fourth stress is a catalyst. So let's start off by talking about concentration. Now, with concentration, we're going to talk about it in terms of reactants and products. So if we increase the concentration of the products, then you're going to see an equilibrium shift. And what I want you to think about is we can think about this mathematically. Kc is equal to the concentration of the products over the reactants. And remember, the equilibrium constant is a constant, it can't change. So if we introduce more products, then the equilibrium is going to have to shift. And so if the number on the top gets bigger, then I'm going to have to increase the number on the bottom. And remember, the number on the bottom means reactants. So if you increase the concentration of the products, then the equilibrium is going to have to shift to the reactants. If we increase the concentration of the reactants, then the equilibrium is going to shift to the products. Now remember, Kc is equal to the concentration of the products over the concentration of the reactants. So hypothetically, let's say Kc is equal to 5. Now, whatever I do, I have to make sure that Kc is equal to 5. So again, hypothetically, let's say the concentration of our reactants is 2 and the concentration of our products is 10. So we're going to have 10 over 2, and that is going to be equal to 5. Well, if we increase the concentration of our products, let's say we increase it to 20. Well, in order to get the concentration, or in order to get Kc equal to 5, that means I have to get more reactants in my system, or I have to decrease the products in my system. And the only way to do that is to shift towards the reactants. Now, if we increase our reactants, let's say we double that to 4, well, in order for my Kc to be equal to 5, I'm gonna have to get more products. And so if I increase my reactants, then the equilibrium system is going to have to shift towards the products. Now let's look if we decrease. If we decrease the concentration of our products, if I have 20, a concentration of 20 for my products, and I decrease it to 10, then I am going to need more reactants. Sorry, I'm going to need more products in order to make sure that I get back to that Kc equal to 5. So the equilibrium is going to shift to the products because we have to get more products in there if we decreased it. If we decrease the concentration of the reactants, then the equilibrium will shift to the reactants. Now you can increase concentrations by adding more reactants or products. When you're decreasing the concentrations, you usually don't take them out. It can be really hard to take something out of a chemical reaction. So a lot of times this can be done by a competing reaction. So let's look at an example. We can look at the formation of ammonia from nitrogen and hydrogen. So we can look at what's going to happen to our equilibrium system if we add more nitrogen, if we add more NH3, or if we remove the hydrogen gas source. So if we add more nitrogen, if I look at my equilibrium system, I notice that nitrogen is a product. So if we add more, or sorry, a reactant. If we add more nitrogen, I'm going to be increasing the concentration of my nitrogen. So we should see a shift to the products, right? If we add more reactants, I now have more reactants than I need. So I need to get more products formed. If we add more ammonia, now I notice that ammonia is a product. So we're increasing the concentration of our ammonia, which is a product. So we're increasing the concentration of our products, and we should see a shift to the reactants. If we remove the hydrogen source, that means we are decreasing the concentration of hydrogen, which means we are decreasing the concentration of our reactants. If we decrease the concentration of reactants, then we should see a shift to the reactants. All right, let's look at pressure. Now, this is very important. The pressure is going to depend on the equilibrium system. So it's going to depend on the equilibrium system. So you can't just say, like, products and reactants. If I increase the reactants, it's always going to do this. If I increase products, it's always going to do this. You have to look at the individual system. So if we increase the pressure, really the only way to do that is by decreasing the volume. Remember, volume and pressure are indirectly affected when you're looking at gases. So if we decrease the pressure, the only way we can do that is by increasing the volume. And the system is going to shift to to the side of the reaction, to the side of the reaction with fewer gas moles. If the pressure is increased. So if we think about it, when pressure is increased, it means that there is more stuff. And so you'll see it shift to the side with fewer gas moles to make more room. So the system will shift to the side with fewer gas moles if the pressure is increased. And remember, we increase the pressure by decreasing the volume. So let's look at an example. We can look at the formation of ammonia again from nitrogen and hydrogen gas. Now, if we decrease the volume, we are essentially increasing the pressure. And on my reactant side, I have 4 moles of gas. And on my product side, I have 2 moles of gas. So what this means is if I decrease the volume, I'm increasing my pressure, and I should see a shift to the side with fewer gas moles. So in this example, will see a shift to the products because there are fewer gas moles. Now, if we increase the volume, therefore alleviating the pressure or decreasing the pressure, we would see a shift to the reactants. Let's look at another example. If we look at the formation of hydrogen fluoride gas from hydrogen and fluorine, in this example, if we decrease the volume, it means we are increasing the pressure. And here I have 2 moles of gas on my reactant side and 2 moles of gas on my product side. So if we increase the pressure, we should see no shift because there are equal amounts of gas moles. All right, let's look at one more example. If we look at the decomposition of water vapor, going to hydrogen gas and oxygen gas, when we balance this out, we're going to have 2 moles of gas on my reactant side and 2 moles of gas, or 3 moles of gas on my product side. So if I decrease my volume, I am increasing my pressure, and we will see a shift to the reactants now because there are fewer gas moles. So hopefully you can see how when you're looking at the stress of pressure, it's going to depend on which system you're looking at, because the system will alleviate that stress by shifting to the side with fewer moles, and that is going to really depend on the equilibrium reaction. When we're looking at temperature, again, this depends on the equilibrium system. Going to depend on the equilibrium system. So you can't just say it's one way every single time. So for an exothermic reaction, remember for an exothermic reaction, we think of heat as a product. So heat is released. So we can think of it as being a product. So in this case, temperature acts as a product. And then we can look at it in terms of concentration. So if we increase our temperature, it is essentially as if we are increasing our products. And just like with concentration, we would see a shift to the reactants. Now, if we decrease our temperature, it is essentially like we are decreasing the concentration of our products, and we'll see a shift to our products. If our equilibrium system is an endothermic reaction, then in this case, heat is being absorbed. So we can think of temperature as a reactant. So if we increase the temperature, it is essentially like we are increasing the concentration of our reactants. And if we increase the concentration of our reactants, then we should see a shift to the products. And if I decrease my temperature, then I am essentially decreasing my reactants, and we should see a shift to the reactants. So in this case, when you're looking at temperature, it really is going to depend on whether the reaction is an exothermic reaction or an endothermic reaction. Now, the final stress we're going to look at is a catalyst. And remember, a catalyst speeds up the reaction by decreasing the activation energy. So what happens is the rate of the reaction for the forward reaction is going to increase, but what also happens is the rate of the reverse reaction also will increase. They can both happen faster. So in this case, the addition of a catalyst will cause no shift. All right, let's look at an example. We have the reaction of carbon with water vapor yields carbon monoxide and hydrogen gas. And then we have delta H is equal to 131 kilojoules per mole. Now, go ahead and pause this video, see if you can do some of these on your own, and then you can come back and check your answers. All right, one of the first things I like to do is write out my equilibrium expression. And my equilibrium expression is going to be Kc is equal to the concentration of carbon monoxide times the concentration of hydrogen gas divided by the concentration of water vapor. Remember, carbon is a solid, so we do not include it in our Kc expression because it doesn't have a concentration. So other thing that I like to make note of is my delta H is positive. So that tells me that this is an endothermic reaction. So T is acting as a reactant. All right. Carbon monoxide is removed. So carbon monoxide is a product. If I decrease this, then I'm going to have to shift it towards the reactants in order to keep our system at equilibrium. So if we decrease the concentration of carbon monoxide, it means we are decreasing the concentration of our products, and we should see a shift to the reactant, shift to the products. I think I started moving on to the next one too quickly in my head. Now the reaction is cooled. So what that means is we are decreasing the temperature, which means we are decreasing our reactants. And if we decrease our reactants, we should see a shift to the reactants. Water condenses. So I know condenses means going from a gas to a liquid, and liquid water is not going to be part of our equilibrium expression because it is a liquid. It doesn't have a concentration. So what's happening in this one is we are decreasing the concentration of our water vapor, which means we are decreasing the reactants. And again, since we decreased the reactants, we should see a shift to the reactants. If we increase our temperature, we already established this is an endothermic reaction. So an increase of temperature is like we are increasing our reactants. So we should see a shift to the products. All right. If we increase our volume, then we are decreasing the pressure. So we'll see a shift to the side with more gas moles. In this case, I have 1 mole of gas on my reactant side and 1 mole of gas on my product side. Right here, plus 1 mole of gas here. So we'll have 2 moles of gas. So if we decrease our pressure, we're alleviating the pressure through that increase in volume. So we should see a shift to the products because there are more gas moles. Now, if we add more carbon, carbon is a reactant, but notice carbon does not have an effect on the equilibrium because it is a solid. So if we add more carbon, we should see no shift. If we add hydrogen, that means we're going to be increasing the concentration of hydrogen. Hydrogen is a product, so we're going to be increasing the concentration of our products. And when we increase the concentration of our products, we should see a shift to the reactants. Finally, if we add a catalyst, remember a catalyst is going to speed up the reaction by lowering the activation energy, but it speeds up the reverse reaction in addition to the forward reaction. So we'll see no shift.